Tech Snippets Today with Joseph Raczynski.
Jens Groth, Chief Scientist at Nexus. Thank you so much for joining me today.
Very happy to be here, Joseph.
Yeah, I'm looking forward to it. All right, so let me sort of pull some ideas together and then we'll launch into some questions and discussions thereafter. Zero knowledge, ZK proofs, ZKPs, ZK SNARKs, Groth 16 protocol. If that all sounds like secret code from a spy movie or a spell from a tech wizard, you're not alone. Those are some difficult concepts that not many people are too aware of. But I'm asking you all to hang on for just a second, because these are magic words that are shaping the future of how our data travels, hides, reveals itself in the digital world, especially as AI balloons around us. So lucky for us, we have Jens here, the very architect behind Groth 16 itself. He's here to sort of demystify these cryptic concepts, show us how privacy can eventually win in the age of information overload, and how maybe even he can convince us how ZK SNARKS isn't just a great band name, but something that can actually be used. So buckle up, privacy is about to get a whole lot more interesting. All right, let's dive into this, Jens. First and foremost, I always love to hear about people's backgrounds, what led them to this space, and we'll start off there.
For sure, yeah. So I can go really far back. I was a student. I was studying math at university. At some point, I felt I wanted to do something practical, and I stumbled on cryptography, and I got really excited about that. And I was very fortunate that, world-leading cryptographer was at my university that could advise me. And eventually, I started doing a PhD, which was a project on voting, internet voting, right? So the idea is that you should be able to cast your vote from wherever you are, right? And you would encrypt the vote to keep it secret and confidential. And then there would be a tallying mechanism that allowed the authorities that were running the election to sort of like decrypt, but in a combined way, so you didn't reveal any individual votes. And there was a problem here, right? And the problem was that if you encrypt it, you can encrypt anything. So you could encrypt the equivalent to, say, minus 100 votes for somebody.
Oh.
Right? Which is horrible, right? Okay.
No doubt.
Right? It's like taking your hand into the ballot box and taking out some votes for somebody. Okay. So how do you solve that? You could solve that with zero-knowledge proofs, right? And the key thing about a zero-knowledge proof is that it can prove that something is true, and it can prove it in a way such that it doesn't reveal anything else. You just learn that, this claim is true, right? So how does that work in a voting context? What you prove, so you encrypt your vote, then you prove that you have voted for a valid candidate. You don't disclose who you voted for, but you just prove that you have cast a valid vote, right? You're not,
right.
encrypting minus 100 votes, right? And that sort of like solves the problem, right? I mean, everybody who's tallying up and getting the result, they're happy because they know all the votes are actually valid, right? And you as the voter, you are happy because your vote remains private, right? So that's a zero-knowledge property.
Amazing. No, even the voting, so let's just stay on this for a second, because I'm really so curious about it. I think voting, when we get to this point in time where this is all clicking and working for people, that's probably, unfortunately, the last thing, though it makes so much sense that people will be like, oh yes, I'm okay with that. One thing that I've always been like, and I love these concepts and what you're working on with zero knowledge, the naming nomenclature for it. Is there a way that we come up with something that's just, it's easier for people to be like, oh, I know what that is, and it makes sense to me, like one word or something, you know what I'm saying? Like, we need to come up with branding around this.
I kind of feel you here, right? It's like zero knowledge here that doesn't tell you so much if you're don't know the field already, right? And in some contexts is a misleading thing. I don't have a good answer to that. I mean, there has been several different things that people have tried in the literature, so calling it SNARKs and STARKs and so forth, which are basic acronyms for fancy types of zero knowledge proofs. And yeah, people have tried, so like the parts of it. So for instance, in the construction, you use something called commitment schemes. Sometimes people have called that blobs, but that also doesn't really tell you
Yeah, I
anything,
know.
right? So
I know.
it's a hard challenge that the field, after many decades of research, have not resolved.
No, completely. All right. So Jens, now you are chief scientist at Nexus. So can you give us a little understanding about what Nexus is, what you're trying to accomplish there, and then we'll bounce off from there.
Yeah, so our focus is really on making the world verifiable, right? So our tagline is sort of like verifiability at internet scale, right? So which sort of like gives you sort of like the ambition that we have, that we really want to, make everything that matters to people verifiable, right? And I think it's in particular something that's sort of the scale of the problem is growing, right? Because, what is internet scale? But, now with AI coming and AI agents, right? I think we're going to see a transition to even more data, even more transactions and interactions being produced, right? And the reason for this is that, AI takes off some of the human work that goes into it, right? I mean, whenever you take an action and produce something, there's some effort that you apply to this, right? But with AI, that effort goes down because now it's sort of like automated. It's the AI that's doing it rather than human that's doing it, right? And I think then we will see this transition to, having more transactions and interactions, because you can have sort of like microtransactions with less value that sort of like is the threshold where humans want to get involved, right? And of course, that then means, okay, now we have even more to verify, right? It's an even more ambitious goal that we have. And the way we're trying to address this is essentially building this distributed supercomputer, right? Which sort of like can help create all these proofs that we think will be necessary.
It's very cool. I love this idea, and I've been sort of touching on it with a few people. I've investigated for years with NEAR protocol as well as ICP, so Internet Computer. So along those lines, how would you say this differs from, let's use an Internet Computer blockchain, which has been
Yeah,
around for a long
and
time?
I know the internet computer blockchain very well because that's where I was working before I joined Nexus,
Oh,
right?
all right,
So
excellent.
so it's not like, so there's and I think the internet computer is great, right? It has really good speed and scale. So there's definitely advantages that ICP can trump it. I do think then that one difference which is important, right, is that we want sort of like to give rock solid guarantees, right? And that's not something you're getting from the threshold system that the internet computer operates, but it's something you can get from zero knowledge proofs, right? It's sort of like, so you get these kind of like mathematical guarantees when you give a proof for something that, it really is absolutely correct, right? It really happened this way. I mean, there's some very minuscule, but we're talking like, in a trillion and a trillion and a trillion and a trillion kind of probabilities that things go wrong, right? And you're cheated. So I do think that we can give a system that sort of like provides stronger guarantees.
Excellent. Okay. So what I've always wondered about is sometimes first movers or original sort of blockchains, if you want to call them that, next to Bitcoin, leaving that alone for a second. You look at Ethereum, you look at Solana, very different, but those are the names people know. So why didn't Ethereum build something like this? Why is Nexus that next layer, the next step forward in this piece?
Yeah, and it's interesting, right? Because I mean, so Ethereum is very much thinking about this now, right? So there's
Yeah.
this like, the new kind of proposals for how it should work that, you would really incorporate verification of proofs directly into the system and use that to prove things, right? And that is basically to address, I mean, it addresses several things, right? But one of the things it addresses is basically the scale. Okay, so now let's go back in history, right? Ethereum started back in the day, right, where people were not aware of this kind of thing even, right? That zero knowledge proofs could be used in this kind of blockchain context. And it was actually first Zcash that introduced zero knowledge proofs in the blockchain space, right? And said, hey, we have this cool technique that is not really that widely applied, right? Which can give you private transactions. So I can prove that I had a coin and, that I spent it, but without revealing which coin I spent, right? That was sort of like the core idea. And it's sort of like, for me, it's very interesting because I've been in this space for a long time, right? So I remember when I was an academic, I was a professor at UCL, University College London, we would have, people from industry coming to us. I would tell, there's this beautiful technology, right? It was very hard to, both explain it because nobody knew what it was, right? And then also, convincing this is something they could actually use, right? And that's sort of like flipped with Zcash, right? They were the ones that sort of like kicked it off, and then it sort of like blossomed in blockchain space, and people have found like lots of beautiful applications of proofs, right? And in particular, right, they noticed that it's not just about privacy, but also scalability is part of like, a core thing that proofs can give you. It simply allows you to scale the verification of all sorts of, transactions in a blockchain much more efficiently, right? And that's sort of like what has then, Ethereum could just execute general smart contracts, right? And eventually they've sort of like gone on this path of like, oh, well, this sounds like, a technique that we could really use to scale things. And people have started building ZK rollups and things like that to scale Ethereum.
It is wild to watch all these ecosystems mature, right? I mean, it's happening quickly, but in some respects it hasn't because Ethereum has been around for so long at this stage. And it's great to see all these contributors, all these different groups coming into the fray. And then you have the layer twos, and they're trying to do certain things that maybe the layer ones couldn't do or couldn't perform at different levels. So all this started to come together, and SWE now getting more and more recognition. And I think what's important that people, I think, have to start thinking about is, and you alluded to this definitely, is that with AI and with all this information that's being generated, likely by agents, right? So agentic AI, agents coming up with new concepts or ideas, or going out and doing things on your behalf, or whatever the case is, and there might be microtransactions. All of that is being performed, and you need a place to store that, or verifiability, like you just described. All of that seems to sort of come together, and that's why all this is sort of hitting critical mass. One of the things I'm really curious about is with regard to your protocol, Groth 16, like how did that come about? Because it's a thing. Forgive me, I didn't know it. I've known all these other ones, but I did not see this one, and I apologize. But I'd love to hear more about that in particular.
Yeah, okay. It's a good question where to start, because there's sort of like been an evolution building up to it, and people in general don't know the background, right? So maybe I'll give you sort of like a very quick tour through so like what is the history of it. So the history of zero knowledge proof started in the 80s, right, where with the invention of zero knowledge proofs, very quickly people came on the idea that, hey, maybe we don't need interaction, right? So the first zero knowledge proofs was like, I have a prover, I have a verifier. The prover sends a message to the verifier. The verifier sends a challenge back. The prover sends some response and so forth, right? And you have this kind of interactive protocol. But people came up with the idea, hey, we can make it non-interactive. So just a proof, boom, done, right? So that was sort of like one development. I sort of like came into this in sort of like the 2000s, right? So and one question sort of like that was puzzling me, and I was a postdoc at UCLA at this time, right, was, okay, so how can we make something that is sort of like efficient non-interactive? Because the techniques were not, were like the efficiency was absolutely horrible, right? And interestingly, just at that time, there had also been some works on something called pairing-based cryptography. And I sort of like combined those two ideas. So it was sort of like, fortunate to be in this situation. I was thinking about, a problem that nobody had solved, right? I kind of like, discovered that there's a connection here, and pairings is sort of like the magical thing that can make some of these proofs work, right? And we sort of started constructing non-interactive zero-knowledge proofs from pairings, right? And like efficiency was like sort of first we sort of like constructed a proof of kind of concept kind of protocol. Then we got something that was like, well, efficient in theory, but maybe not in practice, right? And so like there was several iterations there. Okay. I think the next big thing then, okay, so for all of these proofs here, so think of like you have something complex you want to prove, right? You have this kind of like large, complex computation claim or something like that, right? For all of them, the proof size would grow with that, right? So the more complex thing you want to prove, the bigger the proof is, right? So we would talk like it was very complex, you would have like gigabytes or terabytes of proof size, right?
Wow.
Which is horrible. Again, something you cannot just send around on the internet. So there was this beautiful question, okay, can you do it more compactly, but still based on pairings, okay? So there's a competing technology that didn't have, had some other properties and also had shown that you could do it more efficiently, okay? And this is a problem I solved in Groth 2010, okay, which is a paper that nobody knows about.
Wow.
Almost, right? But that's sort of like where it first came, right? That you could have these kind of like very compact pairing-based proofs for, really big computations, right? And then there's been sort of like an iteration after that of like, coming up with new tricks and new techniques, and there was some beautiful works. There was also not so often cited, but also beautiful paper by Helge Littner from 2012, which improved the efficiency of that construction. And then there was another one in 2013 that improved it even more, and so like became sort of a very well-known technique. And then people started doing implementations. The first implementation was called Pinocchio, and also came up with sort of like even more efficient. And Groth 16 is sort of like, so Groth 10 sort of like started that. Groth 16 is sort of like still, one of the best, right? And they're also like more, really trying to say, hey, what if we really push all these techniques? How small can it be, right? And now with Groth 16, we're down to like, we're talking about a few hundred bytes to prove any arbitrary big and complex computation.
That's amazing. Wow. That you've got it down that small. So is it platform or blockchain agnostic?
So the proof system is, so I would say it has not so much to do with the platform or blockchain or something like that, because really you can use proofs in the blockchain space or outside the blockchain space, and it's not tailored specifically to that. Of course, you need to sort of like, tailor a bit the construction to what is the specific type of things that you want to prove. So in particular, there's a setup that you need to run and prepare in advance. So anybody who knows this setup can go and prove things. And that's all like really specifies what is the concrete type of computation that I'm proving here.
Okay.
So that's the kind of tailoring, right? And then there's, the thing that it's not agnostic about is so like, what are the underlying cryptographic assumptions we're using, right? So people are really trying to sort of like explore this space of like, how can I minimize the assumptions I'm making, right? Because, it is a drawback that people point out with Groth 16 that you have to trust this setup is correct, right?
Okay.
And then people are trying to say, come up with trustless setups where you don't have to trust anybody, right? That you can just go and you can do it. So that's sort of like one parameter that try to differentiate proof systems. Of course, efficiency in various forms, right? It started with computation, but now people also care a lot about memory consumption when you're proving things, right? So that's also a parameter. So those are like many different proof systems depending on what kind of cryptographic assumptions, which kind of setup assumptions, and which kind of efficiency and so forth you want.
Amazing. Okay. So along those lines, if I am, let's say I'm a script kiddie or a vibe coder, and I want to be able to start leveraging some of these, I'm just going to call it zero knowledge. It could be your version, it could be any version, right?
Yeah.
Are there any tools out of the box, be it on Nexus or something like that, that I could then implement or use in a generally easy way rather than knowing all this stuff? So in other words, taking this great technology and making it much easier for people to implement into apps at the app layer.
Yeah.
Are we there yet? Are we a little bit further out? How's that look right now?
We are getting there, and it's really a good question. I think it really cuts to a core of a development that's been here in the field, right? So when I first got into the space, right? I mean, the tool was me. You take a PhD student, you say, "Hey, I want a zero knowledge proof for a voting system. How do I do that?" Right? And And then people have started, coming up with tooling that you could use. And, to begin with, it would be tooling that's like you really have to be an expert and to use it right and so forth, right? What we are working on right now at Nexus, and there are also several other teams that are working on things like this, is what is called a ZKVM, right? And it's really designed to make it as easy as possible to go and implement a proof system. So what it does is it basically lets a developer be a developer in the original sense that they know how to program things, right? This is the computation I want to compute, and now I want to also have a proof that it's correct. Okay, and a virtual machine, that's basically saying, hey, you can compile down to this kind of virtual machine. So that's Java bytecode or RISC-V processing or something like that, right? And okay, and then you just have this kind of like a virtual machine that then executes the computation and out spits out a result. And a ZKVM then says, let's execute the computation, spit out the result, and also give proof that this output is correct.
Amazing.
So,
okay.
So basically you just know some programming language. You just go and you compile it to whatever this virtual machine, run it in the ZKVM, and out comes a proof.
Okay, that is promising. So I appreciate that. All right, I have one question left, but before I do that, is there anything that I've missed? Anything you'd like to highlight about the organization or anything else that you're working on?
Yes. So I can tell you a little bit about what we have been building. Right. So we have this challenge here, right? So we're building a ZKVM, so it becomes really easy to prove things, right? So that's one part of the package, right? But then there's also this question of just the massive scale of everything that needs to be proved. So we've been building this kind of distributed supercomputer to prove things, right? So which creates some more other technical hurdles, right? Because now you have to orchestrate that. Here's a really big thing we want to prove. And it's still expensive to prove things. So it's cheap to verify and the proofs are small, but it is expensive to prove things. So that's why we need build this distributed supercomputer to do that, right? So then now you have to sort of like compartmentalize the work to compute this proof, right? And you have to distribute it on many different machines, right? And they all have to work together, and you have to combine their contributions, and out comes a proof. So that's what we've been developing, and we've just we are running sort of like what we call the testnet 3, which is really a test of this proven network, and we have millions. We have 2.6 million nodes that have contributed to this.
Wow.
800,000 during peak times, right? So it really is on par with various supercomputers in the amount of effort that's going into this, right? So that's just amazing, the response that we've seen.
That's fantastic. I didn't realize the numbers were that high. That is huge. Yeah, there's a lot of blockchains out there that don't have quite the volume or numbers of nodes or whatever the case is. some
yeah,
like
and it's
Solana,
all over
very
the
few.
world, right? That the
Yes,
contributors are from as well, right? So
that's true
yeah.
decentralization. All right, the last question that I have, I'm just kind of curious about, for those of us that have been in this space for 10 plus years, let's say blockchain or AI or both, for me, it's wild to watch all this come together, right? So blockchain sort of sat independently of AI for years, and now it's just a natural merging or marriage of the two, in my personal opinion. I think a lot of people are thinking that way at this stage. But when I go out there and I talk to people that are really not into either one, or now they're into AI because, ChatGPT is something they use to write something or whatever the case is, or they're like, oh, it's the best thing in the world. How do we explain to people that more than likely blockchain is going to be the foundation or a part of the bigger picture of where AI goes, because the agents are going to be running everything and they're going to need a place to verify or to save or whatever you want to say? What, how do we get that message out? Or do we even need to? We just build applications and people will use them and the underlying layers will just do what they need to do.
Yeah, I do think that we need to get the message out. And okay, so let me take a step back, right? So the way I see the AI space as perceived by the public, right? So of course, AI has been around for a long time, many different kind of techniques, and these LLMs is one of those techniques, right?
Exactly.
But they sort of like really, capture people's imagination. They've really seen a lot of traction, so I use, ChatGPT and other AIs every day, right? And it's sort of like becoming ingrained in people's workflows and so forth, right? And I think that's, just going to continue, right? We are in this, super exponential growth in AI technology. What the risk is, right, then is, okay, so we know that AIs hallucinate. We know that you can sort of like create malicious models. So there's a lot of like, risk, right? And deep fakes is also something you can use AIs for malicious purposes, right? So I think we're potentially, on the verge of having this deluge of, untrustworthy information, right? Whether it's, it could be deepfakes where it's sort of like maliciously generated. It can also just be bugs, right? Because you have these hallucinations and things like that. So you just get like lots of buggy data, right? And especially when you sort of like combine them and you have like agents string together, right? And you're getting
The
data from
swarms.
different agents together. One of them has a bug, right? So you need some way to coordinate them, right? You also need some way to rectify mistakes. You need some sort of like ground truth on which you can sort of like, actually build trust, right? And I think blockchain is really the right tool for that. Zero knowledge is really the right tool for that. There's also things like formal verification, which I think is the right tool to use in this context. The problem is it's very difficult in general to convince people that security matters until they have been hit, right? I mean,
Yeah.
who can you get to buy home insurance until they've been burglarized, right? It's so and the concern I have then on a societal level is that, if this really takes off, right, we have all these kind of like, transaction data and things going on, which is all AI generated, right? We can have like, a giant kind of catastrophe happening before we put in those kind of security protocols, just because people were like, let's just go and not think about, sort of like how we sort of like make the core of our systems solid beforehand, right? So I think there's a place for blockchain, for zero knowledge proofs, and for many other techniques, right, to provide that kind of robustness. But yeah, we feel both racing against time, because it really is, I think, a very short timeline. We have to sort of like get that up, right? And so like traditionally, like if you want something to be rock solid and secure, then you spend a lot of time and a lot of effort to make it right. And now it's more like, make sure it's rock solid and secure and do it right now, right? So that's a huge challenge. And we're trying our best. And I hope many other teams and projects also will sort of like take parts of this problem and tackle that.
Well, Jens, I very much appreciate that. It's all on your shoulders. So if this doesn't work out, come back to you. No, I'm kidding. No, but seriously, thank you so much for sharing your wisdom today. All of that you worked on, created. It's fantastic to hear about, and I greatly appreciate the time today. Thank you very much.
It's been a pleasure. Okay, thanks, Joseph.
Tech Snippets Today with Joseph Raczynski.